Okay, we're going to get started here. Make sure you fill out the attendance link, attendance.offsec.club. I'll chill here for a little bit because I think there's some new faces, so just make sure you fill it out so we know you came. Also helps us later if we're pushing out labs and stuff. So we also, as always, have questions.offsec.club. Someone already asked, what is a question? So, classic. You can just ask anonymous questions, and Mark will be up here talking, and then he can answer all the crazy math stuff people have going on. Okay, so this previous weekend was Wild West Hackin' Fest. There were a good chunk of people that are here right now that were also out there. It was a good time. There was a couple of CTFs. How many were there? At least two.
There was a DNS one, and there's the Meta CTF, the
Grim.
CTF, IoT hacking.
So, yeah, that was a fun time. There were all sorts of talks, as you might expect for a conference like this. There was one that I went to that someone was talking about LDAP and Windows vulnerabilities. And he was like, yeah, Kerberos is this crazy thing. And someone talked about a couple of years ago, you can do something called Kerberosting. And I ended up looking that up later. And the guy who talked about it was the guy who was presenting there. So he didn't even name himself. So it was just kind of interesting. All sorts of cyber stuff. What is that motion?
If you want to watch the videos, they upload them. There's actually a Wild West Hacking Fest YouTube channel that you can go watch, so if you feel like you missed out.
Like the talks?
Yeah, the conferences can be kind of expensive to go to, but oftentimes you can find the videos, and Wild West Hacking Fest is one of the conferences that actually just uploads them. They're pretty easy to find.
And all the talks are 50 minutes, and then they have campfire talks, but it's awesome if you want to be what the heck is Windows red team stuff? Where do I start out? They had talks on that, so you can definitely.
Do they publish their CTF stuff too?
No.
I don't think so. Can you still see the problems? Yeah, they hold those under lock and key. They're no one can know the secrets.
I got the crypto one. Look at them.
Oh, RSA 0.5.
Yeah, we want to actually show that.
Yeah, that was a fun time. For the Meta CTF, we had some winners from DSU. The faculty team took first, so they actually got black badges for it. And Chris did a little fun stuff with this picture, as you might be able to tell. The original picture, they all look kind of unhappy except Sean. So it's fun. But yeah, they get black badges, which means they no longer have to pay to go to Wild West. They get to just show up and be like, ooh, look at this badge, and then they get to go there. So, and then we got fourth, us three and Nick Alholina. So we got a free shirt. That was a good time. So, do you remember where THS placed? Were they 8th?
I can look at the school list.
But second and third place were pro CTF teams, and fifth probably was as well. So DSU faculty beat them pretty handily, and we were right behind them.
We're about 3,000 points ahead of everyone. DSU faculty.
Yeah, DSU faculty killed it. If we were moderately okay at web exploitation, we could have done a lot better. But yeah, that was a good time. Programming club tomorrow is some sort of a hackathon. Jared, what else is going on with that? I guess any of the programming club officers.
Just Jared.
Yeah, so it's going to be an hour to make something with a theme that's relevant to tomorrow, being Halloween. That's still to be determined. And may or may not be a prize, may or may not be food.
Wow, that sounds like a very definite, certain planned event.
It'll be a lot of fun. May or may not.
So that's going on. Computer Club is doing a VPN discussion setup. I don't really know what they're going to use. DefSec will be Windows and Linux persistent, so it's the stuff that we like to put on computers, how to actually dig that out. And next week, we'll have someone here talking about, I think one way to describe it is Wi-Fi frame manipulation. So it's, instead of using Scapy, he made his own thing, I believe, and it's pretty cool. And then I think he can both listen and transmit and do weird stuff with Wi-Fi, like beacons and everything. So that should be a good time. I don't know if it's a public thing or if he'll make it public so that other people can work with it. This is probably Logan's slide because it says Mr. Crypto, which is Mark. So after this, Logan, Jared, I'll probably be here too. We can talk about some of the NCL preseason challenges because NCL individual opens up this weekend. So we can go over some of the preseason problems and see what's up with those. Okay, Chris, you got your current event stuff.
I don't know how accurate the first one is. There was like a post that I got in my like feeds that was like "Happy Birthday to the Internet," which doesn't make sense to me. But yesterday apparently was some sort of holiday in regards to that, so it had to do with UCLA. If you want to look it up, all right. First thing, Adobe Creative Cloud leak. So they left a nice database available. So just like 7.5 million email addresses and like your country of origin and some other stuff like that. But that was found by there was a detective that found it, and then they're not sure if that stuff was leaked or not, like how many people actually found it and had access to it, so it's uncertain there. But it's probably, I don't know, better than just like everyone having a copy of the database for sure. So, but yeah, that's a fun one. This was like early October, so TCP Dump, libpcap, everyone can read those, I guess. They had like something like 33 vulnerabilities that they found, and this stuff hadn't been updated in over 2 years, so this is like the first update that they had to do. It was just like some buffer overflow stuff, but that's 33 different vulnerabilities to look over, so it's a good chunk of stuff, but something interesting to think about or check out. But yeah, 2019 stuff. And then NordVPN, I kind of had to mention this one. This was a big deal. So the NordVPN was hacked. It was all like, whoa, because they spend millions of dollars in advertising. So there are a lot of people that are like, you spent a lot of advertising money, but like your stuff wasn't secure. Interesting. But it was one server in Finland that was like, I don't know, I'll call it contracted out. So it takes a lot of like different locations to have like an effective VPN service. So one of the places that they were had connected to their network was a place in Finland. It was kind of a new deal. The server that they set up ended up being vulnerable, sort of like remote management stuff. So I put iDRAC and ILO on there. People probably don't know what that is, but that's like ILO is like HP's default remote management stuff, like out of the box, and then iDRAC is like for Dell stuff. But like the reason why it's a maybe on that is because they didn't like release details on it, which not a surprise there because it's kind of a big deal to be breached. So no details really on that, but there was speculation on that because of the Finland hosting service. That's kind of their thing, was like HP and Dell stuff, like servers and whatever. So, and then also they realized that the attacker would have had access to snag a private key, so they would have been able to do like HTTP, like DNS, man in the middle sort of stuff. But they don't know, and they don't know how many users were affected because they don't keep logs of like what users do apparently. So that was their response to any of that stuff. So yeah, kind of just like and it was all like hush hush for a little while they did an internal audit before they actually released that they had been hacked. So kind of an interesting approach to that, but whether that's right or not, I don't know. You guys can decide that. This one's a fun one too. So there's an Israeli intelligence group called NSO or NISO, I don't know how you want to say it, but Facebook's not happy with them. So they actually abused, so WhatsApp does like end-to-end encryption, but once the encryption once it's been decrypted, this is what they were attacking, was like the decrypted messages and information on like the end of the client. So there were like 1,400 people that were hacked or whatever, where they had gotten the messages for those people. And so Facebook wasn't happy about that. And NSO was just like, it's our business. Like, that's the stuff we do. And Facebook's like, well, here's a CFAA. suing thing that we're going to do for you. So it'll be interesting to see how that works out because it's a company suing a company using CFAA. So I don't know if that's happened before, but kind of an interesting thing. Oh, I spelled apple wrong. Whoops. So this one's a fun one. There's like no details on this. So hopefully soon there's details on it. But all we got was like an application may be able to execute arbitrary code with system privileges. So, but it's these are the vulnerable versions for that. Something with Apple graphics control. That was all that I could find on that one. So, boink. I think that's all of them. Cool. Does anybody else have anything that they found? It's cool. Yeah.
Saw something about the PHP 7 vulnerability.
Oh, okay. Something to look into, I guess. Do you know any more about it, or just? Oh, shucks. All right. Yeah.
So there's been some talk about unfork.
Oh yeah, that was. I didn't put it in here because I didn't understand it fully. Do people know what forking is? I see some heads not. I'll just explain it. So like, you've got a process, and then it's just like, I'm going to become 2 processes. So that's forking. That's a good explanation. They're completely like, Jared's writing that down. So they're completely separated, right? They don't share memory, but they're kind of copies of each other. So, what is NCO? Yeah, somebody put it on there. Oh, so anyways, yeah, so there's apparently some way for, and I think it's for like debugging stuff, where you can unfork processes, which is, it's weird. I don't know. If you're really smart, then you can read about it, like Logan. CV 2019. Is that the
memory
PHP?
spaces? It's like fork splits memory space into 2. Unfork is just trying to like merge them together, which can cause lots of problems. So I'm not sure the point of it, but there's a way to do it, I guess.
I'll just peek really quick. That's going to take a while. So if you really want, I'll say it in the video, but it's supposedly the PHP one is CV 2019 11043 or 11,043. Woo, numbers. So,
What was that last number?
1143.
yeah, 11043. My bad.
Oh.
But yeah, that's all that I had. So we can let Mr. Crypto talk now.
There you go.
Yeah.
This has got an HDMI port though, so I have to carry a dongle. Well, that's exciting.
Grapple, as Chris would.
Incorrectly spelled, I guess.
Sorry about that.
That's okay. I'll take it.
You say as both of us are using a Mac. Has a Mac, yeah.
With an iPhone and a watch, just fully in. All right, so cool. So I'm Mark. I get to chat with you guys for unknown amount of time about unknown amount of topics, but yay! So some of this came up after you guys actually had your own little CTF competition, and only a couple of you actually solved the asymmetric cryptography side of things. So I decided to come in and chat about some of that, but I wanted to keep it fairly friendly because I don't necessarily know all of your backgrounds, and so we're going to start with some cipher stuff just because it's kind of cute. So hooray! So if you're in my 201 class, which a couple of you are, you actually saw this slide this morning. But it does actually give us a nice way to frame this difference between symmetric and asymmetric and bring about inverses and all these kind of goodies that we're going to need. So it may look kind of silly, but there's some meat eventually. So there's a cipher. So there's some garbled up message that connects into an original message. So what is my plain text for that one? Hey, and what cued you into thinking that that said hello world?
2 Qs.
2 Qs? Do you not know any other words that have double letters?
I don't know. It seems like everything was statically shifted.
What'd you say?
The slide before you presented.
Oh, so you cheated, you're saying. Yeah, so this one was pretty easy. I mean, there's a space, so maybe you're led to think that it's actually two different words. That doesn't have to be. I mean, I could have just put random spaces in. I didn't actually say that letters are going to be encoded to the same letter always, so the two Q's could technically come from two different letters, but I kept it friendly, so yeah, this is everybody's favorite. It's Hello World. How is this actually encrypted? So going from the small letters, so the plain text, into the capital letters, the ciphertext, what is the official process here?
Is it a Caesar cipher?
It is, yeah. So it is a shift of what, though? 5, yeah. So I'm shifting everything forward by 5. How many of you guys have seen Caesar ciphers before? Cool, neat. So we'll cruise through some of that. So yeah, we're taking the alphabet, so all the small little letters, so A through Z, there should be 26 of those, and then they match to their little friends, F through E, with the shift of 5. So we get this nice little key that allows us to encrypt something. It allows us to also decrypt whatever we want to go, just depending on if you're going from small letters to big letters. So going small to big is the encryption process, and going big back to small is the decryption process. So here's another one. Here's a phrase. Now you know what the key is, so how do you go in a verse? What's the Y going to become? A T. The M becomes an H. The J becomes an E. The W becomes an R. The J then becomes an E. So that first word here is there. So if you wanted to keep on going, just like this quote, so I threw that one on there. So this says there's only one way to deal with this, and that is to stomp it flat. Does anybody know whose quote this is attributed to?
Mario Brothers.
No, you guys are all too young. It's actually from Optimus Prime. So that's the shirt I'm wearing right now. For those of you that are looking online, it's a picture of Optimus Prime drawn with primes that Anna gave me a nice super duper sketchy link to. So I decided to give them my credit card information, and then they sent me a shirt about 2 weeks later. So that was a good idea. And on the right is just a more stylized one in case you can't see. In case you can't see the actual primes that are underlying it. So hooray, that's ciphers. Ciphers are, oh, somebody said, oh, hi, Mark. So thank you for the room reference. So hooray. Might as well. A couple things that we'll pull up if we want to is, obviously with Caesar ciphers, they're pretty dumb in that there's only 26 ways to encrypt something. Really, there's only 25 because if you don't do anything, it's just extra dumb because you just don't change the letters around. So you can technically spam all 25 or 26 options to see all the emerging shifts and then stare at that list and hopefully see words emerge. And if you look at that laundry list at about row 5 or 6, you can actually see some English words. So you would have a pretty slick way to decrypt that thing. Computers are also really good at staring through laundry lists of words. So as long as you tell it what words look like, you can impose some type of ranking into this. So it'll shove some of up to the top. So you can also see that really the only one that looks like English words is with the shift of 5. So there's some stuff there. That's neat. All right, so shift by 5, just to kind of remind you of how this all emerges. You have little cipher wheels, so you can shift things around. Probably play it around with some of those. If not, you should go take a piece of paper, make a couple nice little wheels on it. This one is encoding the idea of a shift of 5. So it has the little a going to F, little b going to G, and so on and so forth. What we eventually want to do is give these things numbers. So I'm going to start A being 0, and then I go up to Z being 25. So hooray, that's neat, that's extra exciting. The thing that we need to allude to is this idea of once I go around the circle once, I need to talk about how to go back on it. So there is this modular structure. So there's a mod 26. You guys all comfortable with doing modulo stuff? So there's mod 26 because there's, I think, 26 letters in the English alphabet, so we're going to go with that. So what ends up happening is that anytime you jump over 25, you're going to have to reduce back down. So the circle looks really nice. It works like a clock in case you're not extra comfortable with that. If you wanted to add a little bit more structure to it, here's that same key that we had before. I just lined it up with numbers so that when I say shift by 5, I really just mean add 5. So take letters, convert them to numbers, add 5, convert them back to letters afterwards. The letters are dumb, so let's just talk about numbers. The actual encryption function then I'm going to boringly identify as an E. So it adds 5 and reduces mod 26. All right. Yeah, that's not too bad. Well, let's go with that. All right, so here's another random cipher. I funneled it through the same thing that I did before to see if I could brute force this. So do any of those things look like English phrases? I mean, I don't see any phrases there. So what that tells me is that this phrase up above was not encrypted using just a simple shift, so something else was happening. So if I gave you a hint and told you that this was computed by not addition but multiplication, how could you decrypt that message?
Multiply by the inverse.
I could multiply by the inverse. Colin's extra on top of it. What's an even easier way to do it?
Divide by 3.
Oh, you're still thinking way too hard. So I'm telling you how letters are encrypted, so you could just blast through all 26 letters and create a key, and then use the key in reverse, which I think is how Logan did the RSA one and capture the flag last time, was it gave you the encryption function, so to see what happens with all the letters, and then work backwards. So multiplication here is the same. I take letters, I represent them as numbers, I multiply by 3, and then I reduce mod 26. So A is dumb because it just goes to itself. B is a 1, so it's multiplied by 3. So it just becomes a 3. So that tells me that B goes to D from starting at 0. So I can actually create this whole big key. So then I could actually go in reverse. So the K is coming from what little letter? So K is here. So what did K emerge from? An M. So the second letter is an A. Where did A emerge from? A. F is here. That came from a T. What's next? A V. So V came from what? An H. So actually the first word there is math. So hooray. I'll actually show you what that thing comes to in a bit, but this is where I wanted to at least bring about the idea of an inverse. So Colin alluded to it already, is that if I wanted to actually build up the function that goes in reverse. So cryptography is all about building functions that have inverses. I can go one way and then I can theoretically go back the other way. So I need to know how to undo multiplication by 3, which is to say I need to go from this list of numbers up to the list up above. And you can actually cheat and look at this direction to see that going backwards from the B, which is a 1, needs to go to a 9. So what should I multiply 1 by to make a 9? No, hooray. 7. I mean, I guess, for 7s that are defined as 9. Go from there. Yeah, so the reverse direction here is actually going to be multiplication by 9. So the inverse, so the fancy word here, the multiplicative inverse of that little 3 is a 9. And the reason that works is that if you take 3 and 9 and multiply them together, they make 27. And 27 reduces down into a 1, mod 26. So division by 3 works because 3 and 1/3 multiply to make a 1. So 9 and 3 multiply to make a 1 in this fancy mod 26 setting. So the notation there is going to be 3's inverse is 9. And these inverses are going to exist all over the place. Not every single function, not every single number is actually going to be invertible here. So you could think about having the coefficient in front of that little m, so the encryption function. Well, if the 3 was a 0, that'd be an extra dumb way to encrypt something because it'd send everything to 0. There are other numbers that are actually problematic there as well. Does anybody have an example of some number that might be bad as a coefficient, or like the slope?
2.
A 2. Yeah, why is 2 bad?
It's not co-prime with 26. You can't find a thing that multiplies by it to get 27.
So 2 is going to be bad, yeah, because there's some fancy words there. It's not co-prime to 26, so it shares a divisor with 26, namely the number 2. And you can actually see that if you begin to take a number like A, or a letter like A, which is a 0, if you were to shove it into that multiplication by 2, that would go to 0. So it says encrypt A as a 0. But if you also looked at whatever 13 is connected to, 13 is N. So if you're to take the little letter N and multiply it by a 2, so you get 13 times 2, which is 26, which would also get sent to a 0. So you'd get two things that are pointing to the letter A, which is problematic because I can't undo that. But all I needed there was this notion of an inverse. The full-fledged decryption of that one is actually a pretty slick little quote by Gauss. He's arguably one of the top 5 coolest mathematicians of all time. So the quote says, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." So it's an adorable little quote. If you like quotes, I don't know. I like quotes and I like history. So here's another quote by Hardy, who's also an arguably a fairly cool mathematician. This quote's from 1940, which says, "No one has yet discovered any warlike purpose to be served by the theory of numbers or relativity, and it seems unlikely that anyone will do so for many years," which is one of the weirdest quotes ever when you look back on it, of being like, wow, you're claiming that number theory is not going to have any warlike purpose. Well, hold on 30 years, and all forms of public key cryptography is all based on number theory. So it's most certainly connected to warlike purposes, so not necessarily the greatest quote once you look back. But oh well. How many of you guys look at XKCD cartoons? How many of you are going to start looking at XKCD cartoons? So XKCD is a fantastic online cartoon. I don't know, they come out with new ones Mondays, Wednesdays, and Fridays. So here are two of my favorites. I'll let you read them. I actually like the one on the left a little bit more than the one on the right. Yeah, they're extra nerdy and they're extra great. Yeah, the one on the left is talking about Alice and Bob, as we're going to see in a little bit, is that all of these crypto systems always have two people talking to each other, namely Alice and Bob, which are just more interesting than an A pointing to a B. So that's why Alice and Bob emerge. And the right-hand side is just kind of a cutesy, let's just beat somebody up with a wrench because it seems more enjoyable. So the plug for physical security is also important. All right. So ciphers are part of a larger collection of things that are referred to as symmetric ciphers, which pictorially are represented with my terrible drawing here. So you have two people, Alice and Bob, communicating with one another. Alice wants to send some message off to Bob, and she needs to encrypt this with some mechanism to create some random ciphertext, and then she sends that off to Bob. And the hope is that Bob can then understand the message that Alice sent her by actually being able to decrypt it. So for this setup to work, Alice and Bob both have to be in possession of a secret decoder. Classic little decoder ring. And they both have that information at hand. So they can use the key to create the ciphertext, and then the same key is used to take that ciphertext and return it back to plain text. So that's your classic symmetric setup. Examples of this are, well, the shift cipher and the affine ciphers that we just looked at. The Hill cipher, which is basically the same thing but with matrices. Enigma machine, so again, World War II reference. So we then have DES and AES and many, many more. All of these are symmetric, so they require two parties sharing some nice little key. What's wrong with that? Kyle and I want to begin communicating with one another. I'm going to be like, Kyle, let's use this key. I hand him a key and I have my key. And then we begin this communication.
Someone can listen in on that communication. They have the key.
What communication? Our initial chat?
Our key discussion.
Yeah, our key discussion. So the big issue in all of that is this works great and dandy as long as Alice and Bob have a chance to securely communicate with one another to actually share the secret decoder. If I mail a secret decoder off to Kyle, somebody could intercept that secret decoder. Now they have one too. So we have to be able to communicate before this whole process can actually unfold. So that was a problem that dated back to the 1970s. Does anybody know the first algorithm to attack this problem of how do we swap keys? So in particular, a key exchange. Yep. So anybody ever heard the Diffie-Hellman key exchange? Diffie-Hellman were not actually the first people to do it. Originally, it happened in Britain underneath their lock and key organization. So it was like 20 years later, it was like, oh, by the way, Diffie-Hellman released this in 1976, but we actually did it in 1972, but it was confidential at that time, so we claimed it to Diffie-Hellman. So there might have been somebody doing it before it did come out, but the name is still Diffie-Hellman. Roughly at the same time, some other cool individuals emerged. So here are three of them. The middle guy's last name is Rivest. The guy on the left's last name is Shami. And the guy on the right's last name is Adelman. Yeah, so these are the three guys that make up RSA. Their last names are what RSA comes from. And I love this picture of them because it also just looks like it could be a picture right now because you can't really tell this from the 70s, but I mean, maybe you can because he's got some pretty cool collars. I also like that on the backboard, on the chalkboard, they just clearly wrote this, therefore P equals NP, just to troll people. So I was like, I just assumed somebody came by their office and were like, we need a picture for the paper. So they're just like, let's throw this up on the whiteboard and stand in front of it. So if you don't know P versus NP, something to look into. It's an unproved thing that these two things are actually the same. So back in the 70s, three guys were already trolling us. So that's cool. So the RSA is actually a process to be able to transmit information securely. So I'm actually able to send you some stuff even though we have never had a chance to actually communicate. So Diffie-Hellman is this process where we can swap a key. RSA is the first proper public key crypto system. And the underlying stuff that makes it all work is actually not overly complicated. There are a couple of assumptions that one has to make, and then after you have those, you can run pretty crazy with it. So what's going to happen is that I'm going to create this little channel for Alice to have anybody in the world communicate with her. If you want to reverse the roles, just change names around. So Alice has to do a little bit of back-end information, so there's going to be a key generation process. So she's going to pick two massive prime numbers, multiply them together to create this number n. She's not going to tell anybody what prime she used. That would be bad. But she is going to tell everybody what the product becomes. So this number n. That becomes half of her public key. She's also going to release into the world an encryption exponent, which is going to be a nice little number e. Theoretically not very big, but big enough. And she's going to release those two things out into the wild. So anybody in the world can find that stuff. So Bob is going to have some random little message that he wants to send to Alice. And the way encryption works here is he takes this secret little message, he raises it to the eth power, and then reduces that number mod n. There's a little bit of theory that needs to go on as how to do that efficiently. So there's an algorithm that allows us to do modular exponentiation very quickly. It runs in about log n time, so it's really, really fast. And then he sends off that random little ciphertext and oops, everything is set up nicely. So on the back end, Alice has to be able to receive the message. So she needs to undo it. So here's where the inverse comes into play. So the inverse for Bob's little message is to take that ciphertext and raise it to a suitable exponent. The exponent that we use here is this inverse of that little number e, not modulo n, but modulo p minus 1, q minus 1. The fancy way is that that's the Euler phi of p times q, but for now it's just going to be this random decryption exponent. All right, so let's go ahead and see if we can run an example of this to believe that this all works. How many of you guys have ever ran a little RSA example with toy numbers before. A couple of you, a few of you have taken my 201 class, so you'll be doing it in about 2 weeks. All right, so I'm going to pull up some code to see all of this go into play. The bit of code I have here is in a language called Sage, which is basically just Python with some extra stuff added to it. It's run online because I don't have it installed on this computer, so I need to make sure I'm connected. Here's the shift cipher stuff that we did before, if you wanted to look at all that. And I'll give you a copy if you want. All right, so here's the RSA example. So what we need is we need a couple random primes. Does anybody got their favorite prime? 7331. Anna said class with me. So the number 1337 is not prime. But if you flip it around, 7331 actually is prime. Well, I can't use that for Q, so do you have another version for Q?
Devil's Prime.
What?
Devil's Prime.
The Devil's Prime? So another fun prime is the number 1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 6, 6, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and a 1. It's adorable. It's got a 666 in the middle. There's 13 zeros. It's palindromic, so it's the same forward and backwards, and it's prime. So there's my P and the Q. I'm going to multiply those together to create an N. I get to choose an exponent of whatever I want to. The only rule for the exponent is that it can't share any factors with the product P minus 1, Q minus 1. So your best bet here is to take E to actually be prime. And the most common E value that's used is this E, which is 2 to the 16th plus 1. It's the 4th Fermat prime. It is prime on its own. And what's nice is that in this modular exponentiation algorithm, there's this doubling stage. So this tells me how many I have to keep track of. So it's a really common E. Pretty much every piece of software has that E embedded into it. So that's just the one you use over and over and over and over. There's some problems with using that one over and over and over, but that's okay. All right, so I'm going to execute this to make sure everything turns on. So both P and Q were prime, so that was good. What else did I check? To make sure that the GCD actually works, so that's cool. Here's the line where Alice is actually going to compute her inverse. So there's a couple different ways you can compute inverses. Some languages actually have an inverse mod command. A lot of languages have a power mod operator, and if you shove in an exponent of -1, it'll actually do the inverse for you as well. There's a lot of other algorithms. It makes use of what's referred to as an extended Euclidean algorithm, but it's something you can compute fairly easily. All right, so there's the public information that Alice is going to send out into the world. So she's got her number N, which has a lot of zeros in it. It's not necessarily the greatest N because there's a lot of hints as to what it actually is coming from, but that's all right. And then we got our E value, which is 65537, and then I wrote it hexadecimally afterwards just because it looks cool. All right, so now the encryption stage. We need a message for Bob to send, and I'm just going to look at a numeric example. Favorite message? Some number?
Cyber.
That's not a number.
Converted. Jesse's number, whatever that is.
I'm just going to send this message. How's that sound? All right, so I'm going to send that message. So what we're going to do is we're going to take that, we're going to raise it to the eth power, and then we got to reduce that thing mod n. So that becomes our ciphertext. And then we're going to send that thing off to Alice. And we're going to try to decrypt that. And it should come right back to M. That's the whole game. So you send this thing, and you send it right back, and everything is awesome and dandy. So that's an example of showing that RSA actually works. If you want to see why it actually works, take Math 201. Or take my Math 436 class. Or any number of examples. All right, so the interesting part is when I start doing this stuff in reverse. So that's what the flag was in your guys' last competition. There was one that was titled Asymmetric Cryptography, which gave you the N value, told you what the E value was, and then it gave you the ciphertext C. So that's what this one has you do, is that I'm giving you the N, I'm giving you the E, and then I'm telling you what C happens to be. So if that was your information that you were given, how would you determine what the original plain text was? So factor N is one option, and what does factoring N give you?
It gives you P and Q.
It's going to theoretically give you P and Q. Yup.
Guess and check.
Guess and check. So I'm going to factor N. So N factors really nicely on this one because they're tiny little primes. So that tells me that my prime P is 8675309, which again, you guys are too young to know, but that is Jenny's phone number, and it is a prime. And Q is 1 with a whole bunch of 3s, followed by a 7, which is also prime. So that example is something that factors really quickly. All right, so now I got P and Q. Now what do I do? Yeah, so basically, once I know P and Q, I essentially become Alice. In that I can try to create my little decryption exponent and then run that whole process in reverse. So I got to find my decryption exponent, which is, so the inverse of the little E value against P minus 1 and Q minus 1. If I want to print it out, I can print it out too. So there's my decryption exponent D. And then next up, I have to take the secret little message, which is that ciphertext, and I got to raise it to a fairly large power. So I'm going to take that C, raise it to the D, and then reduce mod N. Anybody got a guess of what it's going to become? I actually don't remember what I stuffed it as.
Oh, that number.
Oh, that number. Let's re-execute. Whoop. Uh-oh. All right. Let's look at that little guy. Does that look exciting? Not really. So I was a little bit cuter on this one. So those of you that have taken class with me normally know that I create numbers that look fairly friendly afterwards. This one, it should actually be viewed as a bunch of little blocks of 3. So what I really want to do is I want to take that phrase and view it as a 104, a 101, a 108, and a 111. Why would I ever do that?
ASCII.
Yeah. So those are going to then connect back to something, theoretically a letter. So what I can do is I can convert that back to what it's supposed to be. So the command I can use here is char. If I can type. Maybe I can type. Probably not. Let's just copy and paste this. Anybody guess what those letters are?
Hello.
Yay! So in a lot of the capture the flags, they're not just going to return a bunch of numbers. I mean, that was the one that you guys had in your capture the flag as well, is that it converted, it made a whole bunch of random little things that you then had to convert back to letters afterwards. Yeah?
So over last year there was a CTF, and that was one of the challenges, was getting the numbers and figure out what those numbers end up meaning. What is the process of finding out, like, in this one it's pretty easy because just the ASCII value is just so, back to back. What's the process of finding out what the numbers mean?
So if you're expecting it to be ASCII, it's just going to be blocked into groups of 3, because the largest that's going to be is 256 or something like that. So you're never going to have a collection larger than that. So you can pad with zeros sometimes. So if you have something that's like a 52, you would just view that as 052. So you can run it like that. A lot of times things will be blocked into groups of 8. A lot of these are then going to be represented hexadecimally. So you just have to look at what the possible underlying general structure is, but most of them are just going to be ASCII, at least in the capture the flag versions. They're not going to try to go super duper crazy. So the one you guys had were actually separated by colons, so you knew exactly how those blocked up. In this one, you had to stare at it a little bit and try to get cute. Question on that? All right. So in RSA, there's actually a few other nice little hacks. There's actually a whole bunch of different ways you can run this thing. So the example we just did was one where the n value was really easy to factor. Oh, I got really echoey. Most of the time, you're going to be running with something that's horribly hard to factor. I mean, that's where the security of RSA comes from, is this underlying assumption that factorization is really, really hard. Obviously, quantum computing is going to break that at some point in time. But for now, we can go with this assumption that factorization sucks and it's hard. There are situations that come up that actually give us information that you wouldn't necessarily expect. So one of those is if I have somebody, so Alice, so again, a terribly drawn version of Alice. If Bob tells her to send a message, and he's like, hey, let's be extra secure. Send this once using encryption exponent E1, and then just to make sure that everything was transmitted correctly, let's go ahead and try to send it again using a different encryption exponent, so E2. So on the surface of it, maybe seems legit. It's like, hey, Kyle, send me this stuff, but send it twice and I'll make sure that it came correct. So maybe you think that sounds secure. This is actually a really, really bad idea. Like super duper bad idea. Because once you know that, there's actually a pretty easy way to wrangle out what's going to happen. So there's one little bit of math line, and then I'll go to the actual example. So if the encryption exponents that you were given are actually co-prime with each other, so they don't share any factors, I can find special little numbers u and v that make E1 times u plus E2 times v equal to 1, which then tells you that if you take your ciphertext, the first one, and raise it to the uth power, and C2 and raise it to the vth power, it automatically kicks out the m. So it's this extra adorable way to take things that you don't know anything about the n. So I have no factorization of n is actually necessary, but they funnel back into the m. So let's look at that as an example. So I keep on expecting this type of scenario to occur in a CTF. And if I ever write one, I'm definitely putting one of these in there because it's not as well known. All right, so here's the setup. Here's the n value that we're going to use. It's not easy to factor. So back in the day, there used to actually be what were referred to as RSA challenge problems, and they had cash prizes. So there were these massive products of prime that if you were able to factor them, you got money. This was the hardest of them, which still doesn't actually have a factorization. So nobody actually knows how to factor this number, and that's okay. So that thing is n. Here's it represented base 2, so it's got some stuff. Here's it represented hexadecimally. So it has 617 digits, 2,048 bits, so pretty big, pretty decent. All right, so here's the information that we're given. So I know my random little secret message was encrypted once using that as the exponent, and then it created that garbage for ciphertext. And then the message was encrypted a second time using that as the exponent. So again, there's that scenario of, hey, send me this message twice. Use two different exponents though, because using the same exponent, well, you just would get the same number, and I wouldn't necessarily know if there's a transmission error. So I have two different exponents being sent in, creating those ciphertext. So again, no factorization of n happening, which is nice. So the statement that I had made on that last little slide was, if I can find special little u's and special little v's that make E1u plus E2v equal to 1, then I'm done. So the command here is there's an extended Euclidean algorithm. So again, for those of you, if you haven't taken 201, you'll see that a whole bunch. In that I can find these special little weights. The special little weights for the E1 and the E2 that we had there are numbers 1064 and negative 7023. So just as a quick check, I can compute those. And let me turn these things back on again, because I don't know if I actually have them set. Oh, definitely did not. All right, so there's, why are you yelling? Oh, yeah, whatever. All right, so E1, E2. All right, so those are the commands that definitely do turn out to be a 1. So what I just said is that if I compute C1 to the U, so I'm going to have a power mod of C1 raised to the U mod n, and then I'm going to multiply that by a C2 raised to the V, and I don't actually have those stored, so let me pull those down. Uh-oh. I can type. There we go. What is it? And I'm going to take C2 and raise it to the Vth power, so negative 7023, again, mod n. So those things multiplied together, I'm then going to reduce that mod n. So I didn't have to factor n, I just have to do 2 exponentiations, multiply the result. Any guess of what the message here is going to be? Here's the Devil's Prime. Colin has had class with me before, so he knows that I like to use that number a bit. So it's a really fast way. I mean, it's this thing that you wouldn't necessarily expect, but it's got this really nice consequence on the back end. It's the idea that if you take the same message, encrypt it with 2 different exponents in one step without having to do any work at all, it comes back, which is pretty cool. The other little exploit that we can chat about is along the same line. So here the setup is I want to give some information out, and I want to give it out to a bunch of people. So I'm going to send you a message, and I'm going to send you a message, and I'm going to send you a message. Let's say 3. And what's going to happen is that everybody in the setup is using the same encryption exponent. So let's say everybody has the same encryption exponent of a 3, which is a small exponent. If I were to send the same message encrypted to 3 other people, boop, 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 I again get an immediate identification as to what the actual message is. No work really needed. So what ends up happening here is that it's all based on the idea that we have the exact same exponent. So there's that little 3 involved. So here's 3 random n values. They're a product of primes, whatever primes they end up being. Here are 3 random messages that were created from sending the same message out. So what ends up happening here is that we have to solve or identify a solution to a system of 3 congruences. So I want to find an x value that's congruent to C1 modulo that N1. And I want to find another x value that's congruent to C2 modulo N2. And I want to find an x value that's congruent to C3 mod N3. There's a really easy way to do this. It makes use of what's referred to as the Chinese remainder theorem, as Colin wants to call it the American remainder theorem. It goes back to like this super old school question of counting things that were divisible by random objects. There's this Chinese proverb or something like that. So it's always been referred to as the Chinese remainder theorem, which you will see when you take 201. There's a really nice constructive way to build solutions to that. Sage and a lot of programming languages actually have a built-in Chinese remainder theorem. So you have a list of the C1s and a list of the N1 or the NIs, and then I compute that. And I create that thing. Again, I didn't factor anything. I just solved a system of 3 equations with 3 unknowns, created that thing. And then the very last step to actually identify what the original message was is you take that number and you take the cube root of it. And you're done. So the idea there is that pretty much everybody in terms of software, when they build up some of these systems, there's a really weird echo spot there, is that everybody uses this 4th Fermat prime as being the encryption exponent. So that one that we saw before, way up here somewhere, this guy. So that is the most commonly used encryption exponent. So technically, if you sent a message to that many people, you could run this in reverse and automatically know what your secret message was. The sales pitch for why that exponent is okay is that if you're sending some secret message to 60,000 some odd people, your message is not very secure anyways, because 60,000 some odd people actually know what it is. But this process actually works for that as well. So it's a nice, cheap way to get some of these things to kind of wrangle out, even though you wouldn't expect them to actually be there. And there's a whole laundry list of things like that that emerge in RSA. So there are good primes that one should use when you actually set up an RSA crypto system. There are things that are referred to as not safe primes, which I know is my favorite term ever, is to have a not safe prime. And then there's a whole bunch of these other little scenarios that can emerge that have their own kind of weird consequence as well. There's other issues if you take some really short message. So if what you're dealing with initially is really short, then that becomes really problematic. There's a bunch of different ways you can go about that. And the list is pretty long, but I'll leave it at that. There's some cute little things. Create some in your future capture the flag adventures. You'll definitely see some message encoded twice. How do you go in reverse? But without having to factor. So hooray! So that's all I felt like shouting about. So.
Boom math. Definitely not Chris. So I think that's all we've got.
So I have a question. In the real world, if I'm sending you a document, a Word document, is the entire document encrypted RSA, or how does that work?
RSA is only set up, so the public key side is just to get information so that I can use one of the symmetric systems. RSA on its own is really slow. I mean, compared to all the other encryption algorithms. RSA is just used to get this mutual handshake so that you and I can communicate with one another. Once we have this information, then we use something like AES or DES to actually do all the other swapping afterwards. So yeah, that's a key point, is that RSA is not, you're not going to encode single letters with RSA. I mean, we do in cute little capture the flag competitions because they're nice and fun. But in general, this is just to initiate some type of mutual handshake, and then we have information to do whatever we want to afterwards. Yeah, because otherwise, yeah, it's super duper slow. Thank you. Yeah.
But it's also super secure.
For now. I mean, quantum computing is on the verge, so it's going to die off soon. So yeah, for those of you that don't necessarily know, RSA is 100% getting its security from factorization being hard. So there is an algorithm that's referred to as Shor's algorithm that shows that underneath the assumption of the existence of quantum computing, then there are factorization algorithms there's a way to do factorization in polynomial time, so it can be done very quickly. So things need to change, obviously. So that's where we're at right now, is that there's kind of two big branches of what's going to happen in the future. There are lattice-based ones, and then there are error-correcting code-based ones. There's this nice little competition for who's going to reign supreme. But that's where we're at right now. So yeah, it's decently secure, but thinking about encrypting something and then putting it in some vault and letting it sit there for 60 years and then having to come back to it, well, 60 years hopefully have some quantum computing that you can be like, oh, just kidding, now I know what it is.
Okay, that's all we got for this week, so thanks everyone for coming.
This thing